Alright, so today we are looking at root space decomposition. With the first topic being maximal toral subalgebras and roots. And throughout this, we assume, I believe we're assuming that L is a semi-simple Lie algebra. So, given that L then must contain non-nilpotent elements, otherwise it would just be nilpotent itself, we can find X and L whose semi-simple part XS is non-zero. Is non-zero. So remember that L possesses non-zero subalgebras consisting of semi-simple elements. We're going to call such a subalgebra toral. And so this gives us a lemma similar to Engel's theorem, which states that a toral subalgebra of L is abelian. We may have covered this before, but it's worth having a refresher anyways, going over all this over again. And the proof. Let T be toral. Now we want that the T adjoint of X is 0 for all X and T. Now since the adjoint of X is diagonalizable, given that the adjoint is semi-simple, and we're assuming that our base field is algebraically closed. So we need that the T adjoint of X has no non-zero eigenvalues. Suppose it did that, say, the adjoint of x on y is equal to ay for some non-zero y in t. So y is a non-zero eigenvalue. Then the t adjoint of y on x is going to be negative ay is an eigenvalue vector, of the t adjoint of y of eigenvalue 0. Now we can write x as a linear combination of eigenvectors of our semisimple AT, t adjoint of our semisimple y. So all that's left of the t adjoint of y on x is a combination of eigenvectors of non-zero eigenvalues, if any, which contradicts our supposition there. Now, as with all of these certain types of subalgebras, it seems we have a maximal. Since our toral subalgebra H. Okay, no, that's, I skipped a paragraph. So we're going to fix a maximal toral subalgebra. So I guess this isn't necessarily unique. H of L, so not included in, H is not included in any other toral subalgebra of L. For example, if L is SL, is a special linear group of F, H can be the subset of diagonal matrices. So the matrices associated with the roots along the diagonal. Since H is abelian, which we saw above, it's the family of L adjoints is a commuting family it's a bit unclear what that would be abbreviating. Commuting family of semi-simple endomorphisms of L. So that by linear algebra, the L adjoints of H, the set is simultaneously diagonalizable. So L is the direct sum of subspaces of the form L alpha being the X and L, where I believe X is an eigenvalue of our H of weight alpha. For all H in our maximal torus subalgebra, for A in H star. Notice that L0, where is the set of X in H, set of X and L, whose a bracket with all of H is 0, is just going to be the centralizer of H and L. Which includes H from the above. And where we're going here should be pretty obvious. The set of alpha in H star such that, I guess, non-zero, alpha in H star such that there are non-zero eigenvalues of that weight. A set of roots is denoted as a capital Phi. And its elements are roots of L relative to H and are going to be finite. Thus, we have a root space, or alternatively a Cartan, decomposition, where L is equal to the direct sum of its centralizer in H plus all of the eigenspaces generated by the roots in our phi. All right. For example, We have seen this with L being the special linear n of f. Alright, so we will show that H is equal to its centralizer in L. Then we will describe the set of roots and then show that phi characterizes L completely. Alright. So we're going to start out with a proposition here. So for all A and B in the dual space of our H, of our toral subalgebra, and then we have that the bracket of the eigenspace of alpha and the eigenspace of beta is contained in the eigenspace of their sum. If x is in L alpha, with alpha being non-zero, then the adjoint of x is nilpotent. If alpha and beta are in H star, with a, and they're not just the negative of each other, then L alpha is orthogonal to L beta with respect to the killing form. And the proof we get, for the first, we get that for all x in L alpha, y in L beta, and h in H, the adjoint of H on the bracket of x and y is by the Jacobi identity, each bracket of x on y plus x bracket with H on y, which is equal to alpha of H on x bracket y plus beta of H on x bracket y. These two come from the fact that x is in L alpha and y is in L beta. And this is equal to the sum of these on H acting on X bracket Y. Giving us the first two results actually. Can plug this in to get that the adjoint of X is then nilpotent. For the third one, find H in H with alpha plus beta of H being non-zero. Given that we're assuming that alpha plus beta is non-zero, by definition there must be some element which maps to a non-zero element. Then for X in L alpha and Y in L beta, we have that okay, this is, in this case, it's going to be, this is how we're writing the killing form. The killing form of the bracket of H on X with Y is equal to the is negative of the killing form of X bracket with H on Y. This is just by anti-symmetry and the fact that the killing form is bilinear, and this is equal to, as we have seen, we can cross this bracket along the comma, giving us the killing form of X with H and Y, negative of course. So alpha of H is alpha of H of the killing form X and Y is equal to negative beta of H of the killing form of X and Y, so that alpha plus beta of H of the killing form of X and Y is 0. So, and because alpha and beta is assumed to be non-zero, and we picked H, that alpha and beta of H is non-zero, the 0 must come from the killing form of these two elements. Comes with a corollary. The restriction of the killing form to L0, which, as you remember, is the, if you recall, is equal to the centralizer in H of L and L of H. And this is non-degenerate. So we know that the killing form itself is non-degenerate. We've already shown that. From above, and from above, L0 is orthogonal to all 2 L alpha for every root alpha. If we had some Z in, if we take some Z in LO, orthogonal to all of LO, then by definition, then we have that the killing form of Z with all of L, as we saw above, it has to be 0, giving that Z is 0. Alright, let's go on to our next section on the centralizer of H. So the centralizer of our toral subalgebra recall from linear algebra that if x and y are commuting endomorphisms of a finite dimensional vector space, with y being nilpotent, then xy is nilpotent itself, with the trace of their product being 0. And this leads us into a proposition let H be a maximal toral subalgebra of L. Then we have that H is its own centralizer in L. And the proof we're just going to write C to be the centralizer of L and H. And we're going to have a few steps. Step 1. Is that C contains the semi-simple and nilpotent parts of its elements. So X belongs to C means that the adjoint of X maps H as a subspace of L, I guess just to 2, 0. By previous results, so must both the simple, semi-simple component of the adjoint of S and the nilpotent part of the adjoint of S, X. With the semi-simple part of the adjoint of X being the adjoint of the semi-simple part of X, and the nilpotent part of the adjoint of X being the adjoint of the nilpotent part of X. And so that's everything for that part. Because we know that L is going to contain these, and by this equality they map to 0, so they're in C as well. So that's what we wanted. Part 2 states that all semi-simple elements of C lie in H. If X is semi-simple and centralizes H, then H plus our base field times X, which is an abelian, is toral. And obviously an abelian subalgebra. And this comes from the sum of commuting semi-simple elements is again semi-simple. As H is a maximal toral subalgebra, H plus Fx must just be H, so X must lie within H. Part 3 states that the restriction of the killing form to H is non-degenerate. We pick an element H in H such that the killing form of the element H with all of the subalgebra is 0. Now we want, of course, that H is 0. So if X and C is nilpotent, then as the bracket of X on H is 0, and the adjoint of X is nilpotent, we have that the trace of the product of the adjoint in X and the adjoint of Y is 0 for all Y in H from the preamble. So the killing form of X on all of H is 0. But by the previous two results here, then the killing form of H on all of C is 0. So H has to be 0. Got a bit carried away there. Part 4 states that C is nilpotent. If X and C is semi-simple, then X is an H by 2. And the C adjoint of X is 0, and so it's nilpotent. But if X and C is nilpotent, so is the C adjoint of X is nilpotent, so either way it is nilpotent. Now let C and X and C be arbitrary. Now for X equals the sum of its simple and nilpotent components, with both lying in C, the C adjoint of X in general is the sum of commuting nilpotents, and therefore is nilpotent by Engel's theorem. Since this is for arbitrary X and C, C is nilpotent. Part 5 of 7 states that the intersection of our total subalgebra with the derived subalgebra of the center is 0. Since the Killing form is associative, and the bracket of H, which with C is 0, we have that the Killing form of H with the derived algebra of C is obviously going to be 0, and so by part 3 we get our result. Part 6 states that C is abelian. If not, then the derived algebra of C with itself would be non-zero. As we saw that C is nilpotent, the intersection of its center with its derived algebra is non-zero. We'll say that includes, say, Z. We have from result 2 and 5 that Z cannot be semi-simple. And so has a non-zero nilpotent part Zn in C, and so is in the center C. But then we know that the Killing form of Zn with C has to be 0, a contradiction. And with all this, we get back down to our final part, which states that C is equal to H. If not, then C contains a non-zero, no-potent element, say X. That's by our first two parts. By our preamble and our previous part 6. The killing form of X and Y, which is the trace of the adjoints of X and Y, is 0 for all Y and C, a contradiction. And this comes with a corollary. Which states that the restriction of X, of the killing form, to H, is non-degenerate. Which is what we've seen already. Since C is H, we have that C is H and that the killing form on H is non-degenerate. Yeah. Thus, we can identify a toral subalgebra with its dual space. So each linear functional on H has a corresponding unique, obviously, T of phi in H such that phi of H is equal to the killing form of T of phi and H for all H in H. Thus, our root system corresponds to the subset of T alpha for alpha being a root of H. So we can send these elements over to H essentially and get a subset. And that's, I mean, we're right about an episode length, so I think we'll call it here. I'm liking this section actually. I like this book. Next time we will cover we'll just keep on with this topic here, covering orthogonality and integrality properties. So look forward to that.